Our last decomposition is QR decomposition. Whereas all the other decompositions were based on an eigendecomposition of something useful and interesting, in this case the QR decomposition is actually that decomposition that's used to get the eigenvalues and eigenvectors of a matrix. We'll see that in more detail in Chapter 6. But I want to introduce the QR decomposition here because it is closely related to eigenvalues and eigenvectors. So let's think back to the Gram-Schmidt orthogonalization procedure that we discussed in Chapter 1. So remember that Gram-Schmidt is a technique for turning a set of linearly independent vectors into a set of mutually orthogonal and normalized vectors. And I'm going to use the ideas behind Gram-Schmidt, because that's something we're familiar with, to introduce the QR decomposition. So again, returning to Gram-Schmidt orthogonalization, let's say that we have S linearly independent vectors, U1 through US, and from Gram-Schmidt we would get S orthonormal vectors Q1 through QS using our normal Q notation for orthonormal vectors. We had this relationship between the original vectors U and U hat vectors, which was a step in the process of getting the Q vectors. And so I'm going to repeat that here. So ui hat is equal to ui minus this sum. And remember these sums, there's a term for each of the previous vectors that we've already orthonormalized. And that's why the maximum index here is I minus 1. So you're basically subtracting off a vector whose length is the projection of some vector combination, this inner product here, such that it does this orthogonalization. It takes each new vector and orthogonalizes it with respect to each of the previous vectors that have been orthonormalized already. Then we normalize, so we take the ui hat, we divide by its norm, its length, to get the orthonormal vectors qi. And then that's the output of the Gram-Schmidt orthogonalization. So let's do a little bit of algebraic manipulation on these relationships to show how we can turn this into a matrix decomposition. So let's solve this equation we had on the previous slide, but now solve it for ui instead of ui hat. And we're also going to use this fact that ui hat is simply the norm of ui hat times qi. That's how we got the qi in the first place. So then ui is equal to the norm of ui hat times qi plus the summation of these same terms that we had before. Now let's think about this term here. I'm not really going to do anything with the summation portion here. I'm going to focus on this term to put it into a useful and helpful form. So remember that just as the inner product of ui hat with qj provides a projection of the vector ui hat in the direction of the unit vector qj, so by the same token, the inner product of ui hat with qi determines the projection of ui hat in the direction of the unit vector qi. All right, so just inner products as projections. Also, we have that ui hat is in the same direction as qi, because qi is just the normalized version of ui hat. So therefore, we have that the norm of ui hat is equal to the inner product of ui hat with qi. All right, so this is just some manipulation of the inner products and norms to get this relationship, which of course you can see right here. Now alternatively, we can show that same result by recalling that ui hat is equal to the norm of ui hat times qi. Again, that just comes from the definition of how we got qi. If I take the inner product of qi with both sides of this, we get on the left the inner product of ui hat with qi, and on the right we have our norm times the inner product of qi with qi. But the inner product of qi with qi, well, that's just 1, because they're unit vectors and it's the same unit vector, so the inner product is 1. So therefore this norm ui hat is equal to the inner product of ui hat with qi. Same result as we had on the previous slide, just obtained in a different way. So let's substitute equation 2.56 from the previous slide to see how this helps us. We have from here that the norm is equal to the inner product of ui hat with qi, and then from the relationship on the previous slide, we can rewrite this as the inner product of ui with qi, and then subtract off our sum. But notice this inner product here. It's the inner product of qi with qk. If k and I are never the same, then this inner product is always 0, because they're mutually orthogonal vectors. So because this inner product is 0, the summation vanishes, and we simply have that the norm of ui hat is equal to the inner product of ui with qi. Again, just some manipulations of our vector relationships in order to get that one term in the summation into a useful form. Okay, so now that first term right here I can rewrite as the inner product of ui with qi times qi. And now you can see why we did all that manipulation. I haven't changed anything about the summation here, but you'll notice this first term looks precisely the same as these terms, but now this picks up the ith term, which is excluded from our sum. So now we can include this term in the sum simply by changing the I minus 1 to an I. So now ui is the summation of the inner products of ui with qk times qk. Okay, so all I've done is re-express the Gram-Schmidt orthogonalization procedure into a slightly different form, again with the objective of being able to extract out or see how we can express this in terms of a matrix decomposition. So let's take our original matrix A, and let's say that the vectors ui are its columns. So u1 through us, okay? And then we have our matrix Q, which has the corresponding orthonormal vectors Q as its columns. All right, so same number, same size, A and Q. A is the original U vectors, which are linearly independent but not orthogonal, and Q is an orthogonal matrix. Okay, let's just write out the first several of these so we can kind of see the pattern that's developing. If I is equal to 1, there's only one term in the sum, so that gives us that u1 is the inner product of u1 with qi times qi. Just one term. When I is equal to 2, there are 2 terms. When I is equal to 3, there are 3 terms, and so on and so forth. So if you take a look at this, and again the pattern that's developing, what you can see is that our matrix A, which remember has as its columns the u vectors, can be written as q times r. Q here is our usual orthogonal matrix, and then r here is a right or upper triangular matrix. So the q's take care of these vectors, and the r takes care of the coefficients. So then you can see that the r is indeed right or upper triangular, with the values of its elements being these inner products, which are their coefficients again that you see up here. And then the q is again our orthogonal matrix that has the orthonormal basis vectors, the qi's, as its columns. So you may need to pause here and take a look at this to convince yourself that that is the case. But then that gives us our QR decomposition, which says that our matrix A can be decomposed into the product of 2 matrices, Q, which is an orthogonal matrix, and R, which is a right or upper triangular matrix. So as you can see, one way to actually get the QR decomposition is to first do a Gram-Schmidt orthogonalization. That forms the Q, then you get the R through those inner products, and you have your Q and R matrices. This is a very inefficient way to do it. As we've discussed before in earlier videos, Gram-Schmidt is very prone to the buildup of round-off error because of the way that you construct each of the vectors in terms of the previous vectors. So as you go one to another to another to another, you're building up round-off error as you go. And so it's a very inefficient method in terms of computational time, and it's also problematic in terms of round-off error buildup. So this is not a great way to get the QR decomposition. In fact, we often do the opposite. When you want to get an orthonormal set of basis vectors, as is the case with Gram-Schmidt, one way to do that, and a better way to do that, is to actually get the QR decomposition, and then the columns of Q are those orthonormal vectors. We'll actually see in section 6.5 how we get the Q and R matrices. Again, the idea in part 2 is we want to be able to deal with very large matrices. We want efficient techniques that we can implement on a computer in order to carry out these operations. Now we could, for example, use the QR decomposition to solve a system of linear algebraic equations such as AU is equal to B. So if I have A times U is equal to B, A can be written as Q times R, and I can get the solution in a very interesting way. So remember, R is upper or right triangular, Q is an orthogonal matrix, so I could pre-multiply by Q inverse, which is the same as Q transpose on both sides, and I have R times U is equal to, say, B hat, where B hat is the Q transpose times B. I have Q, I can easily take its transpose, multiply by B, and that gives me the right-hand side vector B hat for this system of equations. Now the point here is that this form of the system of equations is much easier to solve because R is now a right triangular matrix. So you can use back substitution to get the solution of the nth equation, then the n minus first equation, and minus second equation. So you use back substitution in that way, given this triangular matrix, to solve for the solution U that you're looking for. It turns out that this is not a very efficient method. The LU decomposition that we'll discuss in chapter 6 is actually twice as fast. And the reason for that is you actually have to do the QR decomposition, of course, before you can implement this method here. So that's quite computationally intensive, and so we don't actually use it to solve systems of equations. So it might not be clear how we'll use QR decomposition at this point. If we're not going to use it for solving systems of linear algebraic equations, then what do we use it for? I keep making this claim that we use it to get the eigenvalues and eigenvectors of matrices. We'll see that in part 2. It also comes up in part 3 as the basis for doing least squares problems. So we will see QR decomposition a number of times in future sections and chapters of the book. There are 2 more decompositions that we need to discuss. They don't really fit in this chapter because they don't have anything to do with eigenvalues and eigenvectors. However, we will discuss them in chapter 6. One is the LU decomposition that I just referenced a moment ago, and the other is Cholesky decomposition, which we'll look at in chapter 6 as well. So these are used to solve systems of linear algebraic equations very efficiently, to find inverses of large matrices, and they end up being quite useful in practice for very large systems of equations.